Hello everyone, myself Dr. Ranjith Kumar. I'm working as an associate professor in the Electrical and Electronic Engineering Department, Institute of Aeronautical Engineering. In today's class, we are going to discuss about the next concept, which is the choppers. And in this today's class, we are going to discuss about the principle and control strategies of the choppers, as well as the operation of step up and step down choppers. So first, before going to discuss about the principle and control strategies of the choppers, as well as the operation of the step up and step down chopper. So first we will discuss some introduction about the choppers, which means what is mean by chopper, okay, and what are the advantages and how the configuration of the choppers. These points that we will discuss before going to the before entering to the actual topic. So here, just I have listed some important points related to the choppers. So chopper is a static device. Okay, of course, all power electronic converters are the static devices only, and the main function of the chopper is it will convert. Of course, anyway, the chopper is also known as a DC to DC converter because the input is DC and the output is DC. Then what is the need of converting then again DC to DC? Because here the input is the constant DC, this is the constant DC, and the output is the variable DC. The output is variable DC. So this is a DC to DC converter. This is also called as a DC to DC converter, or this is also called as a chopper. And the function of the chopper is it converts the fixed DC to the variable DC. Okay, that is the main function of the chopper. And one of the major application of this chopper is motor control drives. Okay, especially in the DC motors, because anyway the DC motor need the DC supply. So as we know, what are the different controls of the control strategies of the DC motor? Okay, so suppose if you take what is that the variable voltage control. So in that case, the DC motor needed the input as a variable voltage, so that we can get from the or that we can supply by using the chopper, because the chopper, the function of the chopper is the constant DC voltage to the variable DC voltage. Okay, and it is also used in the regenerative braking. Okay, why, I mean how it will use regenerative braking, that we will discuss in upcoming classes. So while we are discussing about the different types of choppers. Okay, and how to make this what is that the DC chopper. Similar like the other power electronic converters that we have discussed in the previous classes, which are the rectifiers and as well as what is that the inverters. Okay, so similarly this chopper is also made with a power semiconductor devices, something like what is that BJT, power MOSFET, and GTO or the thyristor. But anyway, here we are going to discuss the chopper. Okay, or we are going to consider the chopper. Okay, so which is having only the semiconductor device thyristor, and the thyristor based chopper only we are going to discuss here. Okay, and some of the advantages of the choppers also that I have mentioned here, like the thyristor. I mean the thyristor converters. I mean why we are going to discuss. I mean or why we are going to consider the thyristor based converters, because it offers a greater efficiency and a faster response and lower maintenance, and smaller in the size. Even the cost is also very less when compared to the power MOSFET and IGBT, some other switches. Okay, so that's why the basic power semiconductor device, which is thyristor, that is we are going to consider to design these chopper, right? Okay, then here, then we will go for the principle of the chopper. Okay, so here just I have mentioned the basic chopper circuit. Chopper is nothing but we can also just consider as a switch. Then how we are operating this chopper means by operating the switch. By operating the switch only we are going to operate this chopper, right? So we are going to operate this chopper because this is the switch. Okay, so by the operation of the switch is again nothing but turn on and turn off. Okay, so by performing the turn on and turn off, so we are able to get the variable output voltage across the load, and we are giving the fixed input voltage. Of course, the input is DC and the output is also DC. But by performing the chopper operation, which means by performing the switching operation, which is on and off, we are going to get the variable output voltage. Okay, so that's what is just I have mentioned. A chopper is a high speed on off semiconductor switch. The chopper is nothing but a switch. Okay, but instead of that, I mean, some supporting elements also we will use to get the operation, like the diode or inductor. Okay, then when coming to the operation of the chopper, so here let me just consider, or just let me explain the basic principle of operation of the chopper here. Of course, here this is the chopper. Then let me draw the output voltage waveforms for this the basic chopper operation. So here input is a DC, right? So this is, let me consider, this is Vs is the input. So the input that we are going to give, this is the input, the constant DC. So which means here this is the Vs, right? Then this is the time t, and then this is the output voltage. Let me consider, this is what is that, V naught, and then output current, let me consider here, what is that, I naught, right? Okay, just neglect this thing. Yes. So initially, I mean, here if you want to get the chopper operation, just we have to perform the switch. Okay, so that's what perform means on and off. So initially, let me consider the switch is in the off position. So by giving the triggering pulse, okay, or by giving the gate signal, I am just turning on the switch initially. Okay, so let me just consider, I mean, how long you are turning on. So I have just turned it on up to this point. So let me consider this is T on. The time, I mean, the duration of the time the switch is in the conduction mode. So that is the T on. So during this time when the switch is turned on, then the supply, what is that, the load current will flow from here to here, like this. So that you will get whatever the voltage Vs that you are applied, okay, you will get the total voltage across this load. Okay, so let me consider this is L and this is RL load. This let me consider. Then here the same, whatever the amount of voltage Vs that you have applied, the same amount of voltage that you will get across the load, right? Then after that, I have just turned off the switch, okay, by applying some forced commutation, because anyway here the line commutation or the natural commutation will not possible. Okay, so that's why by applying some forced commutation, I have just to turn it off the switch. So if the switch is turned off, then there is no connection in between the supply and load. Okay, and during this time, whatever the current will gradually increasing. Let me just consider the current up to this point. Let me consider the current is gradually increasing. Okay, and when the switch is turned off, okay, so then during the turn on the switch, then this inductor will store the energy in this what is that, by making these terminals plus and minus. Okay, and when it is turned off, then the inductor will discharge, okay, by changing its terminal as a plus and minus. Then the load current will flow, or the inductor will discharge through the freewheeling diode. So but when compared to the actual load current, okay, so because of the inductor, some small amount of the load current will flow. So I mean, so I'm just taking consider up to this point, it is T off. Sorry, let me consider this is T off. Okay, so during this point, this period, okay, so gradually it is decreasing the current, because the small amount of the current will flow through the load because of the inductor. But whatever the output voltage is zero, because here the freewheeling diode will making a short circuit across the load. So that's why the output voltage is zero. So here the output voltage is zero. Right. Then again I'm turning on at this particular moment. Then again you will get the output current. Output voltage is like this. Then during this time again the current will rise. Okay, and again this is T on, and again I am turning off here. This is T off. Okay, so again during this time there is no voltage and the current is decreasing. So like this it will continue. Okay, like this it will continue. Then here the T on is the on period of the chopper. T on is the chopper on period or the chopper conduction period, conduction or on period. And the T off similarly is the chopper off period. Okay, then the total time period of the chopper is T, which is equal to T on plus T off. The total time period of the chopper is, okay, T on plus T off, because as you know, if you want to find any average value or RMS value of this output voltage, then you have to consider the time period. So here the time period is, let me consider here, this is the time period, okay, that is T on plus T off. Then again this cycle is repeating continuously, so that here we are just taking the total time period is T here, then the T is the summation of the T on plus T off. This is the basic operation of the circuit. Suppose if we don't have this inductor, okay, if you don't have this inductor, then we no need to include these diode also, okay. Or if you include this diode also, I mean there is no function of this diode, then here you will get the discontinuous current mode of operation. Discontinuous current mode of operation, which means during the off period you won't get any current. That's why it is the discontinuous current mode of operation, right? So this is how the chopper will operate. Of course, again, how to control the output voltage. How we can get the variable output voltage, that we can understand after discussing the control strategies of the chopper, right? Yeah, this is what is that the output voltage and output current waveforms for this basic chopper. Okay, so this is T on and this is T off, and this is total the time period. And if you want to find the output voltage, then we have to just to find the average value of this voltage, this waveform, so that we will get the output voltage, the average output voltage of this the particular chopper, right? Then how to find the relation between the input and output voltage. Okay, input and output voltage. So for that, here I have just make an equation. The average load voltage, which is equal to the V naught, which is equal to here the V naught, which is equal to Vs into T on by T on plus T off, because during the T on only you are getting the voltage, okay, but during the T off you are not getting the voltage, okay. So but if you want to find the average value, again you have to take the total time period. Then this equation will become V naught is equal to Vs into T on by T. So as I just mentioned, T on is nothing but the on time and T off is nothing but the off time of the chopper or the switch, and the total time period, which is also called as a chopping period, which is equal to the summation of the on and off period, which is T on plus T off. But here the T on by T we can consider as a duty cycle. Of course, here they have indicated with the alpha, but mostly in most of the textbooks they indicated this duty cycle as a delta. But anyway, this alpha is also fine, because to just make clear, okay. So to avoid the confusion between the firing angle and this duty cycle, because as we discussed in the rectifiers, so there the control parameter was the firing angle, and the firing angle which we have represented with alpha, and here this is the duty cycle. Of course, this is also a control parameter, because as you can just see, the output voltage V naught is equal to Vs into delta. Okay, so which means here anyway Vs is constant, this is the input voltage, so the only variable term is this alpha, which is the duty cycle. So by changing this duty cycle, you can get the different voltages. That is how the fixed voltage to the variable voltage. Then how we can change this delta value, because as you can see, this delta is equal to T on by T. So which means either we have to change the on period, T on period, or we have to change the total time period. In both the cases, what is that we can vary the the delta value, that is the duty ratio. Then what is the range of the value of the duty ratio here? The minimum and maximum range. The minimum is anyway 0 because the T on can be 0. Okay, if you don't turn on, then it will be 0. Then if T on is, suppose if T on is equal to 0, then the duty ratio T on by T off, or T on by T, sorry, which is equal to 0. Okay, then the output voltage V0 is equal to Vs into delta. So here if delta, which is nothing but Vs into 0, so which is nothing but 0. Because of course if you didn't turn on the chopper, then how we can get the output voltage? So that's why here 0. Then what about the maximum value of the delta? Right. So here the maximum value of the delta is, anyway, the T on is always less than T. Right. The T on is always less than T, because as we know, T is equal to T on plus T off. Okay. So in this case, suppose if T off is equal to 0, then T is equal to T on. Okay. So which means here, instead of the T on, you can just substitute T, then delta is equal to this T by T, which is equal to 1. So then the maximum value is 1. So which means the delta you must choose, the range of the delta is 0 greater than, what is the delta less than 1. This is the range of the duty ratio. So by changing the duty ratio in between 0 and 1, you can change the output voltage. You can change the output voltage value. Like if you say substitute 0.1, you will get 1, 0.2 and 0.3 or something like up to in between 0 and 1. So this is the basic operation of the what is the chopper. So how we are getting these V0 is equal to Vs into delta, that we will discuss clearly when we are going to discuss about step up and step down chopper. Okay. So this time you just understand. Okay, try to understand. Okay, so what is T on and what is T off, and what is the total time period, and what is the parameter that we use to change the output voltage. Okay, so that is the duty ratio. So what is the equation? How we will get the duty ratio? That is duty ratio is T on by T. Okay, like that. Just try to understand these points. Right? Fine. So the next, the methods of control. Of course, anyway, here the parameter is duty ratio, but what are the different types of methods to control this duty ratio? So here there are basically mainly two different types of methods are there. One is time ratio control. We can also call it as a pulse width control, and the second one is the current limit control. Okay, which is also called as the frequency modulation control. Right, and again here the time ratio control can be divided into two different methods. Okay, so which is based on the frequency. So one is the constant frequency time ratio control, and another one is the variable frequency time ratio control. Then we will discuss one by one in detail about these different types of control methods. First one is the constant frequency system, or the constant frequency control. So as we know, just now we have discussed, there are time period, total time period T is there. T is equal to T on plus T off. So here the name itself, it is showing the constant frequency system. So as we know, T is equal to 1 by F. So which means if F is constant, 1 is already constant, then T is also constant. So which means we must take the total time period as a constant. Okay, and by keeping the time period as a constant, we can change either T on or T off. Because anyway, if T is constant, if you change T off, then automatically T on will also change. Or if you change T on, then automatically T off will also change. So that's why instead of 2, any one you can change by keeping the total time period as a constant. Right. Then here you can see these are the two cases. Okay. So in these two cases, how the output voltage is vary, that because already just now we have discussed the V naught is equal to delta into Vs. Okay, so let me consider here, let Vs is equal to 10 volts. Okay, so in this case, let me consider here in the first case, okay, we are keeping t as a constant in both the cases. So that's why here you can see the time period, total time period is constant. So let me consider here t is equal to again 10 milliseconds, right? So in the first case, case 1, here the t on, okay, so we are by keeping the t, we are changing the t on. Okay, by changing the t on, we are going to change the output voltage. So how it is changing, let me by taking the two cases. So in this case, let me consider here t on is equal to some 3 seconds. So that automatically, because total t is 10 seconds total time period, so if t on is 3 seconds, then t off is 7 seconds, right? Then as we know here, V naught is equal to, okay, so delta is t on by t into Vs. Okay, so here t on is 3 seconds and the total time period is 10 and into Vs is again 10. Okay, so then 10 will get cancelled, then you are having 3 volts. Okay, and in the second case, let me consider case 2, because here you can see when compared to the first case, in the second case the time duration is high. So let me consider reverse way here, t on is equal to 7 seconds, so that automatically t off will be 3 milliseconds, because the t is constant here 10. Okay, so as we know, t is equal to t on plus t off. Okay, so according to this formula, if we consider t on is equal to 7 seconds, then t off will be 3 seconds. Then again V naught is equal to, here t on is 7 seconds, okay, by t is again 10 milliseconds into the Vs is again 10, because input voltage is constant, okay, and t is also constant. So then this 10 gets cancelled, then here V naught is equal to 7 volts. So you can see by changing the on period, okay, so we are going to change the output voltage, because when you consider the t on is equal to 3 seconds, here you are getting the 3 volts, and when you consider t on is equal to 7 seconds, then here you are considering 7 volts, because from this equation also we can simply understand V naught is equal to t on by t into Vs. Okay, so here Vs is constant and t is constant, so V naught is directly proportional to t on. So by increasing the t on, then the V naught will increase. Same happen here, you can see. So here when t on is equal to 3, here 3 volts. When t on is equal to 7, here 7 volts. If you consider t on is equal to 5, then 5 volts. So this is how the constant frequency control system. In the constant frequency control system, so we are making the frequency as constant, so which is nothing but the time period is constant. Then by keeping the time period as a constant, by changing the t on, we are going to control the output voltage, right? So this is about the constant frequency system. Then yeah, that's what here, of course I have taken some other examples, but anyway, right? Then the variable frequency system. In the variable frequency system, what we will do is, anyway, if the frequency is variable, is nothing but again the time period is variable. Then what we have to keep the constant, any one of the parameter we must keep the constant. Okay, so then here I have making the t on as a constant, t on constant, okay, and I am varying t is variable. T is variable, right? So that's why here you can see in the these two cases, here the total time period is up to this, but here the total time period is this one only, up to this point only. Okay, but in the both the cases the t on is same, that you can see. Okay, so again, which means V naught is equal to t on by t, okay, into Vs. So here t on is constant and Vs is constant. so that V naught is inversely proportional to 1 by T. Okay, so which means if the T is increasing, then the voltage is decreasing. Because here you can see, when you are increasing the T, if you are increasing the T is nothing but here indirectly T off is increasing. Okay, so here in this case, when compared to here, let me consider here it is T1 and here it is T2. As we know, as we can see from this waveform, this T1 is greater than T2. Okay, so which is nothing but here, let me consider here T of 1 and T of 2. So T of 1 is also greater than T of 2. Okay, so by keeping the T on, I mean in another way also you can make it possible. Okay, so you can just keep T off as a constant. Okay, and then you can change T. That is also possible. Here there is no what is the condition that we must constant only T on. We can also make it T off as a constant. Okay, and by making the T off constant, you can vary T. That is also fine in this control. Okay, so this is how the variable frequency control method. Then the current limit control method. Because just now, I mean, before we have discussed what is that the basic operation of the chopper. In the basic operation of the chopper, so the current waveform that we have discussed, it is about like this, right? This is the current waveform. So which means here this current waveform having the two limits, okay, which means here it is always varying in between the two limits. So this is the one upper limit and this is the lower limit. So the upper limit can be, I mean, we can make it as a I maximum, and the lower limit it can be make it as a I minimum. So by controlling this I maximum, I minimum also, we can control the output voltage. Because by controlling these I maximum, I minimum, we can control turn on and turn off, so that we can also control the output voltage. So how means here, just I have mentioned, when the current exceeds the upper limit, here this is the upper limit. Okay, so when current exceeds the upper limit, okay, the chopper is switched off. That's why here turn off. So there is no output voltage. And when the current reaches to the lower limit, here this is the lower limit, then the chopper switch is turned on, so that again the load current will get. This will what is that repeatedly continue, so that you will get the chopper operation. So in second case, let me consider the maximum limit is here only. And let me consider here this is the maximum limit. So which means when it reaches to the maximum limit, this point, so at this point only the chopper will switch off, so that you will get only this voltage. Like that, here the on and off time will also depends on the minimum and maximum value of the current. So by changing by controlling the minimum and maximum value of the current waveform, we can also control the output voltage of the chopper. Okay, so this current limit, what is that control is possible with constant frequency or the constant TR, which means in the constant frequency and the variable frequency, in both the cases it is what is that possible. But this method is used only when the load has energy storage element. When the load has energy storage element, which means when the load having the inductor, okay, then only you will get the continuous current mode of operation. Otherwise, you won't get. Okay, so in this case only we will get the minimum and maximum limits. Okay, so if there is no energy storage element in the load, then let me show you how the load what is that current. So let me consider here it is the load voltage V0, and the I0 will be also same something like this, right? So in this case, what is the maximum and what is the minimum value? How we can see? Okay, because the minimum is 0 again, so that's why only this method is used. Okay, when the load has the energy storage element, so that during the off time the energy storage element will what is that cause to flow a small amount of the load current, So that's why the load current will not become 0. So it will become like this. So it will vary in between the minimum and the maximum limits. So this is about the the current limit control, right? Yes. And then next, the classification of the choppers. Here mainly the classification of the choppers is depends on the two parameters, or in two different ways that we can based on two different parameters we can classify the choppers. One is depending on the output voltage. Okay, depending on the output voltage, which means whether the output voltage is greater than the input voltage or less than the input voltage. So based on that we can classify the choppers. In that, first one is the step up chopper. Okay, so step up, which means the output voltage is greater than the input voltage, then that type of chopper is called as a step up chopper. V0 is greater than, sorry, here V0 is greater than Vs. So V0 is always greater than Vs. Okay, irrespective of the duty ratio value. For the duty ratio value from 0 to 1, okay, for all values, the output voltage is always greater than the input voltage. So in that type of converter is called as a step up chopper, or also called as a boost converter. Then the second one is the step down converter, or we can also call it as a buck converter, the reverse way. When the output voltage is always less than the input voltage for all values of the duty ratio, then that type of converter is called as a step down chopper or the buck converter. And the next one is the step up or step down chopper. Okay, so which is also called as a buck boost converter, which means by using this chopper you can get the output voltage is less than input voltage, and also the output voltage can be also make it as a greater than input voltage, but that is depends on the duty ratio. Which means, suppose for a duty ratio of 0 to 1 or 0 to 0.5, okay, in between 0 to 0.5, then it will act as a step down chopper, and from 0.5 to 1 it may be act as a step down chopper. So based on the duty ratio value, you can make it step up or the step down chopper. So that is the buck boost converter. The combination of these two is a buck boost chopper. Then the second classification is depending on the direction of the output current and the voltage, right? So which means the direction is nothing but again plus or minus. Okay, so the class A chopper, class B, class C, class D and class E choppers. So the class A chopper can be also called as a one quadrant chopper, which means it can be operated in only the single quadrant, and the class B is also a one quadrant operation. So it can be also operated in only single quadrant, but of course the different quadrant which the class A is operating. Okay, which means let me consider here this is minus V0, and this is the V0, and this is I0, and this is the minus I0. So the class A chopper will operate in the first quadrant, which means irrespective of the delta value. Okay, so the class A chopper is always operating the first quadrant. So let me consider here, this is the first, and this is the second, and this is the third, and this is the fourth quadrant. So the class A chopper will operate in the first quadrant, and the class B chopper will operate in the second quadrant. Only in the second quadrant. And class C chopper is a two quadrant operation. Okay, so which means it can operate in first quadrant as well as the second quadrant, 1 and 2. So according to your requirement, by using the same chopper, you can shift from first to second and second to first quadrant, which means the voltage is always positive, but the current direction is sometimes it may positive and it may negative. That is depends on your application, you can change. Then class D is also a 2-quadrant chopper, but again the 2 quadrants are 1 and 4, which means 1 and 4. Okay, so the current is always positive, but the voltage is positive and negative. Okay, we can get the positive as well as the negative by using the class D chopper. Then when coming to the class E, this is a 4-quadrant operation, which means by using the single chopper, we can operate in the first, second, third and fourth quadrant. So according to our application, we can operate this by the single chopper in different quadrants, which means here both V and I are positive, and here what is that, V is positive but I is negative, and here what is that, in the class C, okay, AB, right? So V is positive but I is positive as well as a negative, and in this in the class D, I is always positive but V is positive and negative. Okay, so in class E, all kind of operations that we can get. Okay, so one is plus plus, yeah, plus plus, plus minus, minus plus, plus minus minus, all 4. So which means VI, VI, VI and VI. This is the class E chopper. Then we will discuss one by one. Okay, so first we are going to discuss about the step up chopper. So this is the basic structure of the step up chopper. So here the step up chopper having one chopper switch and one diode and one inductor and the one capacitor. I will explain what is that the function of each what is that device present in the chopper. Okay, but before that let me explain the operation of the chopper. Okay, how what is that the output voltage is always greater than the input voltage, right? Yes. So again here also we have to draw the output voltage and current waveform, so that let me just try to draw here, or I have already drawn. Let me explain the operation here simply by using that circuit. These are the output voltage and the current waveforms. Okay, right. So initially, first initially the chopper is in the off position. Okay, first we have to turn on the chopper. So just I have turned on the chopper. Okay, I have turned on the chopper by giving the gate signal to the thyristor. So when the chopper is turned on, okay, so what is the output voltage? Because here this is the output voltage. So by turning on the chopper, okay, then the load current will flow in this way only. So these chopper switch will making the short circuit across the output voltage. So that's why the output voltage is 0 when the thyristor is turned on. So that's why here you can see the output voltage is 0. Okay, and when coming to the current here, that you can see here it is gradually increasing. This is the source current only, because in the load the load current will be also 0, because there is no connection in between the source and the load when the chopper is on. Okay, so that's why here the load current is also 0. Then during this time the inductor will store energy, okay, by making the terminals as a plus and minus, right? Then in the second case, we are turn off the chopper switch. Okay, then the source is connecting across this load, as well as the inductor will also what is that because it is stored, so it will what is the discharge through the diode D and load. Diode D and load. So which means the voltage V0, which is equal to the Vs plus here the voltage across the inductor, okay, that is VL. So that's why here V0 is greater than Vs. V0 is greater than Vs. So during this time, of course, some current will flow through the load. So that's why here this is the current waveform. Okay. So then, of course, because of the inductor, initially the current is high, and when it is going to discharge, then the current gradually decrease. So that's why here the waveform is like this. Then again the chopper is turn on. Okay. Then the inductor will store the energy. Okay, because while discharging it will change. It will what is that? Change the terminals like plus and minus. Then in this way it will flow. Right. So this will repeatedly happening, so that you will get the output voltage and output current. This is the operation of the step up chopper. So by connecting the inductor, okay, in series with the source, so we are making V naught is greater than Vs. Of course, the mathematical derivation also I will explain. Okay, how the V naught is greater than Vs. The same points I have just mentioned here. Just we can. I'm just going to read, and if some point is needed to explain, then I will explain. The step up chopper is used to obtain a load voltage higher than the input voltage, of course, and the value of L and C are chosen depending upon the requirement of the output voltage and current, which means if you need higher output voltage, then you have to take the higher value of the inductance, because so that it can store more energy. Okay, so while discharging it can dissipate more energy, so that's why. And when the chopper is on, the inductor L stores connected across the supply, so that the inductor will store the energy, so that the inductor current I rises in the inductor, and stores energy during the on time, during the switch on time. And when the chopper is off, anyway, the inductor I is forced to flow through the diode D and the load. Okay, and then that's why here, of course, this L into di by dt is nothing but the VL, the voltage across the the inductor. So here V is the input voltage, so the output voltage V naught is equal, just simple, what is that, the simple KVL that you can apply. Okay, the simple KVL that you can apply, then you will get this equation, that V naught is equal to V plus L into di by dt, right? So that V naught is greater than V. So actually this C is to get the continuous output voltage. Okay, of course, because here we are just neglecting. Okay, so that's how the operation of the step up chopper. Then how we are getting the V naught is always greater than Vs. Okay, which means the average output voltage. So here the average output voltage that we are going to derive based on the inductor. Okay, based on the inductor. So here, for that, let me consider here the output voltage. The output voltage. Okay. So here, when the CH1, which is the chopper, is on, when the chopper is on, okay, so then the voltage across the inductor VL is equal to V. VL is equal to V. Therefore, the energy stored in the inductor, which is equal to V into I into T on, because the energy stored in the the inductor will store energy during the T on only. Okay, so how much energy is stored means it depends on the on time, so that's why V into I into T on. So let me consider this is equation number 1. And next case, when CH1 is off, so during this time the energy will dissipate. Okay, or the energy is supplied by the inductor to the load. Okay, so then in this case the voltage across inductor VL, which is equal to the total voltage V naught minus V, because just now we have discussed this is from V naught is equal to VL plus V, right? So from this equation VL is equal to V naught minus V, right? So V naught minus V. Then the energy stored in the inductor, again in this case, sorry, not energy, the energy supplied by inductor, which is equal to the total voltage here it is V naught minus V into I into T off, because the energy will supply during the turn off time. Okay, so if you neglect the losses, okay, then the energy stored is equal to energy supplied, right? So the energy stored is equal to the energy supplied. Okay, so in this case, just I'm making equate the equation 1 is equal to equation 2, so that here V into I into T on, which is equal what is that, V naught minus V into T off. Okay, so just what is that, simplify this. If you simplify, then here V naught, which is equal V into T on plus T off, because here if you send this one, then if you take V what is that as a common, then V is equal to T on plus T off by T off. Okay, T on plus T off by T off. And as we know, here V naught, which is equal to V into T on plus T off, is equal to T. Okay, T on plus T is equal to T, and here as we know, T is equal to T on plus T off. Okay, so from this T off is equal to what is that, T minus T on. Okay, T on plus T off. So T off is equal to T minus T on. Then here we can make T off is equal to T minus T on. Okay, V naught is equal to, then here the V naught, which is equal to, if you take T as a common, okay, if you take a T as a common, then in numerator and denominator, then V naught is equal to V into, if you take T here numerator and again in the denominator, then here it will be 1, and here 1 minus T on by T. So here T will get cancelled. Then we can make it as V naught is equal to V into 1 by 1 minus T on by T is equal to delta. So this is the output voltage equation in case of the step up chopper. Okay, V naught is equal to V into 1 by 1 minus delta. So for any value of the delta, what is that, anyway as we know, what is that, this term should be always positive, because here the delta value is in between 0 and 1 only. Okay, in between 0 and 1 only. So even though if it is 1, 1 minus 1, 0, okay, so 1 by 0 is infinity, so that V naught will get infinite. Okay, so this is how the V naught value, but V naught which is will never less than the V in this case, right? Then the step down chopper. In step down chopper, again, of course, there are two different what is that ways. One is the continuous and discontinuous current operation. So let me just consider this is very simple step down chopper. So just forget about the current, whether it is continuous and discontinuous. I will explain. Okay. So here also very simple. When the chopper is on, then you will get the output voltage, and when the chopper is off, the load is disconnecting from the supply, then there is no output voltage, right? So when the chopper is on, you will get the output voltage, which is same like the source, whatever the voltage that you are supplying, the same voltage you will get across the load. And when the chopper is off, the supply is disconnecting from the load, so that's why there is no load voltage. Of course, there is no load current also. Load current is also 0. Then when coming to the average output voltage, so here these are some terminology. As we know already, VDC is the average value of the output are the load voltage, and IDC is the average value of the output or the load current, and T on is the time, what is that, turn on time, and T off is the turn off time, and T is equal to T on plus T off, that we know, that is the total period or the period of switching or the chopping period. And as we know, F is equal to 1 by 2, that is the frequency of the, what is that, the chopper switch or the chopping frequency that we can consider. As we know already, just now we have discussed VDC is equal to V into Tn by, because this is the principle is same, something like that, the basic chopper operation that we have discussed at the starting of the class. Okay, so in this case, what is that, the V naught is equal to delta into Vs. Of course, here they have indicated D. Of course, in different textbooks they follow the different terminology, but here in this class I am following the common terminology, that is the delta, the duty ratio. Okay, so by changing this delta value, then V naught will change, and in this case the V naught is always less than the Vs. V naught is always less than the Vs. Of course, anyway, EDC is equal to VDC by R. VDC just now we have calculated. I mean, instead of V naught, here they have considered as a VDC. Okay, so VDC is always less than V. Similarly, we can find the RMS value. Okay, the RMS value is again, as we know, the general equation VRMS, which is equal, what is that, 1 by T into integral 0 to T. Okay, so here, what is that, the output voltage equation is V naught square into dt, okay, whole to the power of 1 by 2. So here the total time period is T again, and the limits are 0 to T on, because as you can see here, from 0 to T on you are getting the conduction period. So that's why here the limits, the limits are from 0 to T on into V naught square. Then if you simplify this, then you will get the V naught, okay, or the RMS value of the output voltage, which is equal to root delta into V. Root delta into V. Similarly, the output power P is equal V naught into I naught. Okay, but I naught is equal V naught by R. Then the output power that we can, what is that, in terms of delta, that P naught is equal to delta V square by R. And the efficiency, okay, so which is V naught by IDC. This is how, I mean, the effective input resistance of the chopper. Okay, anyway, this is, we can neglect this time. Later we will discuss. Right. So this is how, I mean, you can derive any, what is that, chopper RMS voltage as well as the power and all. So this is all about what is that, the choppers. So in this class we have discussed what is chopper. Okay, and the chopper is also called as a DC to DC converter, right? So the function of the chopper is fixed, what is that, DC to variable DC, and the basic structure of the chopper that we have discussed, and basic principle of the chopper also we have discussed, and the different control strategies of the chopper also we have discussed, like the time ratio control or the pulse width control, and the what is that, the current limit control. Again, in the time ratio control, the constant frequency control and the variable frequency control, okay, that we have discussed. Then later the classifications of the classification of the choppers also we have discussed. Okay, and the classification, we can classify the chopper based on the two parameters. One is the output voltage, another one is the direction of the output voltage and current. So based on the output voltage, we can, what is it, classify into three. So one is the step up chopper, another one is the step down, another one is the what is that, the step up and step down chopper. And the step up chopper we can also call as a boost converter, and the step down chopper we can also called as a buck converter. And the buck boost converter, that we can get the output voltage is less than input voltage, and the output voltage we can also get the greater than input voltage. Then based on the direction of the voltage and current, we can classify into 5 groups, that is class A, class B, class C, class D and class E. So in the 5 groups, the class A and class B choppers are the single quadrant choppers, and class C and class D are the 2 quadrant choppers, and class E is the 4 quadrant chopper. Right. And after that, we have discussed the principle of operation of the step up chopper and the step down chopper. And we have also discussed how to derive the average voltage equation of the step up chopper and the step down chopper. These are the things that we have covered in today's class. In the next class, we will discuss the remaining choppers, which are based on the direction of the voltage and current, which are the class A, class B, class C, class D and class E choppers. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.